Welcome, my dear J26 students, and on to the lecture number 3 of Electromagnetic Induction. One of the most crazy chapters because it needs nice visualizations and diagrams, and of course, very fundamental concepts. Just Faraday's and Lenz's law, and the entire chapter builds up. So, very conceptual. And we are now on to the final phase. We are doing inductors today. Also, the concept of self inductance, mutual inductance, energy stored in it, and all those series parallel combination, all these things will complete in today's session. So make sure you watch the lecture till the end and stay subscribed so that you do not miss out on the next chapters. And if you have not yet checked out the playlist which is there on the channel, please do that, because it's right over here as you're watching this video. Go to the home page, you'll see class 12th syllabus playlist for chemistry, physics, mathematics, and the same thing for class 11th standard syllabus, physics, chemistry, mathematics. All lectures are arranged sequentially. Go through it, and we are right now on to this particular lecture, inductors, right? And also there is a very important thing. First of all, smash the like button and subscribe if you have not yet done that. MVSAT registrations are on, so make sure you are checking that out. Yep, the MVSAT registration link is over here. This is the scholarship admission test which is happening, on 4th, 5th October, 11th and 12th October. Any of these dates on most of the centers in all the cities spread across the country. So you will definitely find your city. Just register. Lots of scholarships, prizes to be won, cash prizes, rewards. Plus, you will get a detailed report card, and also you will get to know where you stand at the national level. Okay, so even when you register, you are getting a lot of free material, so please do register for it. It's very important. And yes, today is also the last day for registering for the JEE Advanced batch or your Sigma batch for JEE 2026. Sigma batch for making sure you go from zero to hero, and if you are already at some average level, then you should go for the JEE Advanced batches, which is the Ekalavya batch. All right, so today is the final entry point closure. So make sure you register for the same. Okay, so let's begin, guys. I hope you guys are all ready for it. Hello, Kevin. Good evening, Anime. Hi, everyone. Welcome, 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 welcome. All right. Fair enough. So, guys, concentrate and don't just keep chatting among yourselves. Yeah, focus on the class, right? All right, let's move. So, let's talk about what is this inductance. Okay, what is this inductance? Let me explain this to you. If you have some kind of a mass which is lying flat over here on some surface, and you want this mass to move, okay, you want this mass to move with some velocity. It is in motion. So from rest, you want to get it into motion. This process will involve the application of some force, and this mass will resist to change its state. That resistance to the resistance to change the state, from rest to motion, or from motion to rest, or from changing the direction, this particular resistance to change the state, that is called as inertia. That is called as inertia, if you remember from 11th standard. And the way you measure inertia in case of mechanics is via the mass, and mass is nothing but the amount of matter. It is nothing but the amount of matter which is there. So if this rock was very heavy, it will be very difficult. It will resist to change the state more. If the mass is very light, very small stone, it will be very easy for me to change its motion. So how easy or difficult it is for me to change the state, that is decided by inertia, which is the mass, which is the quantity of matter, right? Now in electromagnetism, here is the logic. Imagine you have a circuit, and in that some kind of current is flowing. After some time, let's say more current or less current will flow through it. Okay, more current or less current will flow through it. The current will change. All right. So right now the current was less, maybe the current is less, and let's say now the current is more in this process. So in this situation, when you're changing the current, there will be some kind of resistance to change the state, or to change the, I won't say the state, to change the current. Current is like velocity over here. Just like velocity was 0, now it is more. Here velocity is replaced by current. Current has changed, so here velocity had changed. To change the current, that resistance to change the current is called as inductance. Is called as inductance. This is that property of that electrical circuit. So this is an electrical property. And the device which creates, or device, or that box, or whatever, that wire, the winding, any component, that component which creates that inductance, that particular component, that particular component is basically called as an inductor. That component is basically called as an inductor. So inductor has inductance. Inductance is the property of resistance to change the current, and inductor is that component or the device which has that property. So in real life, everything has some inductive, capacitive, resistive property. It's a combination of all the three. Resistance we have seen, capacitance we have seen, inductance is the final component. And they're in different proportions, and they behave accordingly. Let me give you a simple example. Say we have a switch like this, and maybe there is a bulb over here, something like this. There is a bulb over here, and you are measuring how much current is flowing through it. And you know, I have applied some voltage difference across it. Okay, I have connected it to a battery. Maybe I have connected it to a battery, something like this. In the second scenario, that same switch is there, that same bulb is also there. I'm also measuring the current, but this time there is only one small change. I am bringing a component which is called as the inductor. I'm bringing a component which is called as an inductor. By the way, the symbol of an inductor is this. Usually you will see this is the symbol of an inductor. Okay, this is the symbol. Like resistance has that symbol, capacitor has a symbol, inductor has a symbol of that coil or that winding. So I have an inductor inside this. That's the only difference between this and this. Now what happens is, I close the switch here also, I close the switch here also, and let's see what's the difference, and let us see what is the difference in the current in both the scenarios. This is very interesting. Okay, so this is current, this is my time, current versus time. Right now, when the switch is off, it's very straightforward. No current will be there as long as the switch is off for some duration. So I'm just keeping the switch closed. So this is the duration when the switch is or rather not closed, sorry, it is open. That is why there is no current. Okay, it's open. The moment you close the switch, what will happen is instantly the current is going to jump and some current will flow in the circuit. So this is when the switch is closed, and you will see there is a immediate jump in the current. This is in this scenario, but when there is an inductor, what does inductor do? It resists the change of the current in the circuit. So you will see that the current won't jump like that. Rather, it will jump like this and eventually it will attain that particular value. That is how it will behave when the switch is closed. That's a big difference. You can see that resistance, that hesitation is there. It is not instantly jumping. Are you seeing that, everyone? Imagine now you decide to close the switch back again. So if you close the switch, immediately the current will fall in this scenario. So you will see zip, the current will come down. Again, you have opened that switch is opened. But here you will not see that. It will not drop down directly. Rather, it will take its own sweet time to go down. So it will go down like this. It will go down like this and it will become zero. So that is how it works. There is some resistance. It is not going down instantly. Are you now feeling what an inductor is? How many got the feel of the inductor? How many got the feel of that particular inductor? How many of you got the feel of the inductor? Quickly, let me know in the chat box. Right away, right now. Yes, everyone. It makes sense what an inductor is doing. It is resisting the change. Very good. Excellent. Amazing. Let me know in the chat box. And yeah, random students will be timed out or blocked. No space for random bakwas, random things. Hi, Kamal. All right, Annie. Perfecto. Samiksha. Welcome. Hello. Good evening, guys. Okay. Now that we got the feel of what an inductor is and what is inductance, let's understand the two kinds of inductors which are there. There is something called a self-inductor and self-inductance, and second one is called mutual inductance. Okay, self and mutual. So, what is the difference between the two? Let me explain. What is the difference between self and mutual? Okay. See, imagine that we have a wire which is carrying some kind of a current, and imagine somebody decides to fluctuate that current. The current is made to go up or down. So I have an ammeter to measure the fluctuations, and somebody decides that, I'm going to fluctuate that current. I'm going to make that current go up and down. So whenever there is a change in the current, that change in the current opposes the same current within that same wire. So any kind of change over here, any kind of change which is happening over here, the change in the current is opposed by itself, That particular property is called as self-inductance. Self-inductance. It is like saying you are watching something, maybe a lecture right now on YouTube, and somebody is passing by, some TV is on, some music starts playing somewhere. You slowly start looking, somebody's trying to change you, but you think, no, I should focus on JEE. You push yourself and you focus on the lecture. So you are opposing your thoughts or deviating. So that is like self-inductance. Okay, I hope that kind of makes sense. The other one is mutual inductance. Now, what happens in mutual inductance? Let me explain that. See, imagine again, you are having that wire which has some kind of variable current, changing current, and there happens to be another normal wire beside it, another wire, another device, another, some winding beside it. So any change which happens here, so a change in the current, so basically a change in the current over here a change in the current over here affects the other wire, affects the other wire, that or other conductor, that is basically your mutual property, mutual inductance. You are watching the lecture now, you start looking outside because some music is playing, your friend comes and he opposes you, hey look man, focus on the class. That is like mutual. Or you tell your friend, hey look over here, you are opposing any kind of deviation change. So self is when you oppose any kind of change within, mutual is when you oppose any kind of change in each other or the other wire or the other conductor. Okay, I hope this is absolutely clear. Hi study, hi Sudha, welcome everyone. Okay, so now first let's focus on the property of self-inductance and how to measure self-inductance and energy stored, combination, everything. So let's focus on it one by one. Okay, so how do I define self-inductance and how do I understand it? See, I'll tell you a simple way to look at it. I'll tell you a simple way to look at it. Imagine there is a coil. Okay, imagine this is a coil over here, and this coil is right now carrying some kind of current. This coil is basically carrying some kind of current within it. Whenever a coil carries current, what will it produce, my dear warriors? What will it produce? Obviously, it will produce some kind of magnetic field. So there will be some kind of magnetic field which will be produced in that particular coil. I'm just showing few of these lines over here. It's like a solenoid, so that's how it will be. And yes, the same field lines will continue over here. So might as well think of it like this, dotted line, because it is inside the coil. The same field lines will go like this. Okay. So this is the magnetic field due to the current. When this magnetic field passes through the coil, it will produce a magnetic flux within a coil. Now imagine somebody decides to change the current. How can you change the current? Many ways are there. You can change the resistance, you can replace the battery, you can change the battery, whatever. You can do so many ways for changing the current. So if somebody decides to change the current, if okay, if what are we doing? If the current is changed, what will it directly affect? Think about it. If the current is changed, then immediately the magnetic field immediately will change. The magnetic field changes. If the magnetic field changes, it is passing through the coil. So obviously the magnetic flux changes. Magnetic flux will change. And what happens when magnetic flux changes? By Faraday's law, an EMF is induced by our Faraday and Lenz's law. Faraday's law, and this EMF opposes that particular change. And why does it oppose that change? Because of Lenz's law. Lenz's law. So now can you see any change in the current is being opposed by inducing an EMF opposing that changing current by inducing EMF. This clearly tells me it's an inductive property. So hence there is a self-inductive property. Hence there is a self-inductive property of that particular coil. Self-inductive property of that particular coil. Is this clear? Is this logic absolutely clear? It is self-resisting any kind of change which is happening within the coil. If the current tries to increase, it will not like, it will try to oppose it. If the current tries to decrease, that will also not be like, it will try to again increase it. So it will always try to resist any kind of changes. So it is a self-inductive property. Now, to measure how much is that self-inductance. To measure how much is that particular self-inductance, there is a simple way of doing it. What you need to do, you measure the flux through the coil. So you find the flux which is linked with the coil, or basically that inductor, let's say I call it phi, and you will see that it will always be proportional to the current passing through it, to the current which is passing through it. If the current increases, field increases, flux increases. You replace that constant of proportionality, with an equality. That constant is then called as coefficient of self-inductance, or just self-inductance. This is just called self-inductance. Okay, this L is just called as self-inductance. So phi is Li, is the formula to measure how much is the self-inductance. Now, a lot of times people ask me, sir, if current increases, will L increase or decrease? Sir, if flux increases, will L increase or decrease? My answer to that is, if you increase the current, flux will increase, or if flux is found to increase, then it means current would have increased. But by no means increase of current means decrease of L, because I and L are not related directly. The reason is L is a separate independent property of that inductor. So depends on depends on the windings, how many windings are there, what is the shape, whether it is circle, ellipse, a square coil, all right. Also the geometry of it, what is the length of it, what's the area of it, and sometimes also you might put some material inside it. So whatever magnetic material you are putting inside, all these things decide the self inductance. Okay, so if I increases, phi will increase, L will only depend on the windings, geometry, shape, size, etc., nothing else. So having said that, sir, what is the unit of L, sir? Okay, flux we all know is measured in Weber. Webers or Tesla meter square, and in current is obviously measured in ampere. So naturally we will then get the unit of inductance. Weber by ampere, phi by I is L, that is nothing but Henry. So a Henry of inductance is when a flux of 1 Weber is produced by an ampere of current. Very straightforward and simple. Okay, when 1 ampere of current is passed and 1 Weber of flux is produced, then the inductance of that inductor is said to be 1 Henry. The symbol, how we represent it, remember, is like this. This is the symbol of an inductor in an electrical circuit. Like resistor was like this, capacitor was like this. So inductor, wherever that property is there, you will show it with L, how many are Henry, with that small coil over there. Okay, it's round, not straight, because if you make it straight zigzag, it will become a resistor. All right. Now that we understand it, we can take that equation, which is this one. Phi is equal to Li, magnetic flux is Li, and differentiate it on both sides. So I'll get d phi by dt, and over here I'll just put L, and over here I'll just put di by dt. Okay. Now what the hell is d phi by dt? Rate of change of magnetic flux, but I think I know what it is. Rate of change of magnetic flux is nothing but the EMF which is induced. Oh, so the EMF which is induced is L times of di by dt. This is all magnitude wise. So strictly speaking, I will do one thing. I'll just put E induced and I'll put mod symbol to avoid any kind of confusion over here. And here also I'll put di by dt derivatives mod. L is always positive, so don't have to put mod. So this is giving me the magnitude of the EMF which is created whenever the current changes. The meaning of it. See bro, very simple. If current changes, flux changes, EMF is induced. I want to see how much EMF is induced across the terminals of this inductor. So if you tell me how quickly the current is changing, I multiply it with the inductance, I can tell you how much EMF is being produced by that inductor. Very simple and straightforward. Now, this particular EMF, please remember the direction, the direction of the induced EMF is always going to oppose, is or I will say opposes, always opposes the change in the current, the change in the current. It always opposes any kind of changes in the current. That is how it is directed. So what do I really mean by that? I will demonstrate that to you via three different scenarios. Imagine we have an inductor like this. In the first case, the current is increasing. In the second case, the current is constant. And in the third case, the current is decreasing. The current is decreasing. Here the current is constant. Here the current is slowly increasing from 1 ampere to 2 amperes to 3 amperes. Here if it was 3, it is maintaining 3 always. Here from 5 amperes to 4 to 3 to 2 to 1, like that is slowly decreasing. So what will happen? See, because the current is increasing, you can say, forget the inductor. This is as good as saying it's an equivalent. Instead of that inductor, think of just a battery. Think of just a battery which will oppose it, meaning something like this. Meaning just something like this. So replace that inductor with a battery which will oppose that particular current like this. This is that E induced opposing that current. Why? Because current is increasing, you have to oppose it. You will not allow it to increase so easily. So this EMF is going to oppose it. The value of this EMF is given by L di by dt. Very simple. The value of this EMF is given by L di by dt, and you can put that 5 volts, 10 volts, 7 volts, whatever voltage you get from here, and then just put it here instead of that inductor at that instant. That's it. So that is a replacement of the inductor. If the current is constant, think what will happen. Di by dt, derivative of a constant will become 0. This will become 0, this will become 0, LHS, 0 volts. So 0 volts battery means it's just like a simple wire. It's just like a simple wire. It will not resist only anything. Whatever current is going, just go, man. Like it's okay. You're not changing, right? So I'm not bothered. So it will not do anything. It will be just like a wire. But if you ask me over here, current is decreasing, inductor will say, I will oppose that also. And you will try to increase the current. So how do you increase? By assisting the current. So the induced EMF will always help a decreasing current. So that is how it will be. So again, if you know di by dt, you know L, you put it, you will get the value, whatever 5 volts, 3 volts, you put it in the same direction of the current. So this is how the direction of the induced EMF is. So the induced EMF behaves like a battery, either to help it or to oppose it, or just like a 0 volt battery, which is like a wire, depending on whether the current increases, decreases, or becomes constant. Is that okay? Let us see some questions based on this. Let us see some questions based on this. Imagine, I tell you, there is a flux which is linked with a coil of 24 Weber when 3 amperes current is passed. Find inductance. Find inductance if Now 6 amperes is passed, then the new inductance and the flux is how much? So this is your first question. Let's see how do we solve it. As per the given scenario, the flux linked with a coil is given, current passed is also given, inductance is asked. That means phi is equal to Li is my equation which I have to use. This flux linked is given to be 24. Inductance I do not know. Current is given to be 3 amperes. Therefore, inductance will be 24 by 3, which is 8 Henry. So 8 Henry is the inductance. Very simple and straightforward. Now the second part of the question. If the current is changed, what will happen to the inductance and the flux? Well, flux is nothing but L multiplied by I. This L will not change. It only depends on the geometry, the shape, the material, everything else. So it will not change. It will be the same. It will be the same. But if you are doubling the current, what will happen? The flux will also double. So if current is made 2 times, obviously the flux will also become 2 times. So if this is 6 amperes, obviously this will no longer be 24. This will be 48 Weber. So 48 Weber will be the answer for the new flux. Inductance will still remain the same. That means it will still be 8 Henry only. Okay, it will still be 8 Henry. It will not change. Everyone clear about this? Hi Sindhusri, hi Kana, welcome everyone. Hi Swita, everyone understood. Keep answering in the chat box. I want everybody's answers. Okay, perfecto. Let's see the next question, my dear students. Imagine the question says there is an inductor and there is this battery over here. This inductor is of 2 Henry and there is a current over here, which is given to be a function of time as, let's say, t cube amperes. This is, let's say, 5 volts. This is, let's say, 5 volts. Question is, if this particular terminal is measuring, let's say, 20 volts, can you figure out what is the voltage at this terminal at t is equal to, let's say, 2 seconds? At 2 seconds, can you figure out what is the voltage at that particular terminal? Very nice question. Let's think about it. Current is a function of time. That means current is changing. And the moment current changes, I realize this inductor is not going to like it. It's going to oppose that change, whatever it is. This battery is there normally. Okay, this point is 20 volts. This point's voltage is asked. So maybe first job will be to convert the inductor into a battery. But to do that, we need to know what is the induced EMF. And we all know that the induced EMF magnitude is nothing but L times di by dt. What is the value of L? It's 2 Henry. So just put it over here. Derivative of the current. That means derivative of t cube. What is the derivative of t cube? It is 3t square. That means this will be 6t square. But the question is at 2 seconds. So the EMF induced at 2 seconds will be 6 multiplied by 2 square. 2 square is 4. 4 6 is 24. So 24 volts. See if this is okay, everybody, till this point. I just substituted the value of the time over here, which is 2 seconds, because that is what the question demands. 2 square is 4. 4 6 is 24. Okay, just simple derivative. What this means now is you can forget this circuit and convert it into a much simpler circuit like this. How? Observe. This is 20 volts. Okay. There is a battery over here. As you can see, the current is increasing. Inductor will not like it. It will oppose it. So it will behave like a battery which will oppose it, whose value is 24 volts. And over here, you will have another battery of 5 volts and that's about it. Now this point is V1. Now is it making sense? Everyone, it is now looking like a simpler question, not so complicated. Now we will be able to do it. L is self-inductance. We are doing self-inductance only, Kevin, now. Okay. Pritija, tomorrow you have 11th standard class. Okay. 6 o'clock class of mine. All right. What do we do over here? How do we find it out? See, guys, if this is 20 volts, use Kirchhoff's concept. If I go from here to here, what will happen? If I go from here to here, this point's voltage will be how much? I'm going from higher to lower terminal, so it will be 20 minus 24. From here to here, what will happen? Whatever that voltage is, 20 minus 24, I'm going from low to high. That means I have to add. So plus 5. So how much will it be? V1. Think about it. 20 minus 24 is minus 4. Minus 4 plus 5 is 1. So this will be 1 volt. That is the answer. So this is how you can convert such a question into a much simpler looking problem and solve it. Is that okay? Understood? Let's do one more question coming up on your screen. Let's do one more question coming up on your screen. Here it is. Let's say we have been given an inductor of 4 Henry. Then there is a resistor of 2 ohms. And then there is this battery like this of 10 volts. Okay. And let's say it's been given that this is grounded over here. And somehow there is some kind of current which is flowing of 5 amperes, and this current, the rate of change of current, rate of change of the current is, example, 0.5 amperes per second. Question is, find this voltage V1. How much is this voltage V1? That is the question. So again, based on Kirchhoff's law, you can see it, very obvious. What do you need to do? Convert this circuit into a simpler circuit. That is the first thing you will do. So first, look at the inductor. All right. And the current. Oh, sorry. I need to mention one thing though. When the current is changing, whether it is increasing or decreasing, that needs to be mentioned. So the rate of decrease, the rate of decrease of the current is given to be 0.5 amperes per second. Okay, fair enough. Let's start, guys. So EMF which is induced inside the conductor is given by L times di by dt. The inductance value is given to be 4 Henry. The rate at which the current changes is 0.5. So that means this will be 2 volts. But be careful. Here the current is decreasing. If the current is decreasing, the inductor will not like it. It will try to help it. So it will help it by assisting it in this manner. So this will be 2 volts. Is this absolutely clear? If you compare it with the previous problem, here the current was increasing. So it will try to decrease by opposing that change. Here it is decreasing. So it is assisting it. Same sign convention which I mentioned it over here. Yeah. If it is increasing, it will oppose. If it is decreasing, it will help it. It will strengthen it, like Lenz's law. Okay. Now this point is grounded. That means this is 0 volt. It's obvious. This is a resistor. Obviously, inside a resistor, there will be a voltage drop. I will take care of it. So this is 2 ohms. And the current at that moment is 5 amperes is given. Okay. And of course, this is 10 volts. This is 10 volts. And you have to find how much is V1. See, logically speaking, I mean, if this is 0, I'm going from low to high, use Kirchhoff's concepts. So the voltage over here will increase by how much? 0, whatever is there, plus 2. Okay, 0 plus 2. Here, I'm going in the direction of the current in a resistor, so voltage will drop. So voltage will drop. So whatever we got over here, 2 volts, I have to do minus IR. So I is nothing but 5 and into resistance, which is 2, which is going to give me how much? 5 2s are 10, 2 minus 10 is nothing but minus 8 volts. Here this was just 2 volts. So 2 minus 10, which is minus 8. Again over here, what is happening? Again, I'm going from high to low, plus to minus, so negative. So whatever voltage I got before, I have to further subtract 10 volts. So this will be minus 18 volts. So that is the answer for V1, minus 18 volts. How many of you got it? Yes. Putting capacitor also, we'll just add one more thing. That's it. Hey, I'm coming every day, man. Shreyas, what are you saying? I'm coming every day. My health is good. I'm all fine. Yeah, I'm coming every day over here. You can just see my live class. And yeah, see, yesterday I took one very killer session. Now, many students did not like it. They messaged me personally, sir, what is wrong? Sir, are you fine? Do you have a headache? Are you ill or something? Because, sir, you made alien invasion and all of that. But then I remember one recent movie. I don't know if you have seen it. I think it's called Don't Look Up. I think it stars Leonardo Capri, if I'm not wrong. Have you seen that movie, guys? Yeah, it's an amazing movie. Don't Look Up. So what happens in that movie is there's some asteroid which is coming, and some scientists tell that there is an asteroid coming, and people are so busy and so misguided, or they are so disoriented, and you can say that they are so engrossed in not distinguishing what is truth and what is lies, and they are being manipulated by the media and so on and so forth, that they don't realize that whatever the scientists are telling, it is the truth. They say, oh, you are chumma saying it, oh, it's fake, this, that, nobody believes. The asteroid comes closer, the scientists want that we should, do something about it, maybe change the path, or, prepare for it, make bunkers, whatever. People are like, no, no, you guys are crazy, this is all lies, this is conspiracy theory. The comet comes even closer, you can see it in the sky. Still, people are like, no, this is some agenda by the government, some conspiracy theory, it can't be a comet, and this and that. And the comet finally strikes and wipes out the entire planet. So, I don't know, somehow I got that feeling. Oh, you should see that movie. Anyways, now that we understood how do we convert an inductor into a battery, let's move ahead to another question coming up on your screen. Oh, we have that question actually over here. Yeah, see, in the coil, the current, this is JEE previous year question, the current changes from -2 to +2 in 0.2 seconds and induces 0.1 volts. What is the inductance of the coil? So voltage, inductance and current. There is only one equation like that. EMF induced is L times di by dt. But here I am interested in the average value of that EMF, because the current changes in a large interval of time. So I will use delta I by delta t, everything in the mod. Okay, I'm not interested in the signs over here. All right, so I want to find L. EMF induced is 0.1 volts. Okay, and what is the change of the current from -2 to +2? A lot of people do this, 2 minus 2, and they say 0. That is wrong. It is actually 2 minus of -2. That is the correct way. It's like velocity was here and it is reversing. So the change of velocity will be 2 minus of -2, or change of momentum, mv minus of minus mv, 2 mv. So the same concept is used here. Delta t is nothing but 0.2. Okay, so this will become 0.1 is equal to 2 minus minus means it will become plus. So it will become 4 by 0.2. So therefore, my L will become 0.2 into 0.1 will become 0.02, and this particular number 4 will come below. So what is this? This is becoming 2 and 4. This will become 2, right? So 0.01 by 2, or this is basically half, okay, or 0.5. So this will become 0.005. And where do we have 0.005 over here? Yes, we have it right over here. This is 5 into 10 to the power -3 Henry, which is 5 millihenry. That's it. That is the answer over here, 5 millihenry. Is that clear, my dear warriors? How we got it? Yeah. Harish, gravitation will take some time. Okay. So TN elections in March 2026, will April shift prolong to May month? No, no, it will not happen. I'm so glad, Divya, you loved the way I taught, and please continue watching the classes. Make sure you guys are subscribed and keep following the classes, and In case you want to watch any other lecture which has not been conducted, you can check out my old playlists as well, right? Nurture, Pathfinder, Roar, so many things are there. Cool, well, brilliant question. Okay, but main concept was this minus minus part. Many kids make that mistake. Wanted to highlight that. Okay, there is some battery which is connected to a coil of some ohms through a switch drives a constant current in the circuit. The switch is opened in a very quick interval of time. The EMF induced across the coil is 20 volts. So the inductance of the coil is. Let's understand this. Okay, the battery is connected to a coil. The coil has some resistance. Okay, perfect. This is that battery and the switch is there like this. Coil resistance 6 ohm, inductance not known, battery 12 volts. This is my switch. There is some current. How much current is flowing? Oh, that's not given. Not needed also, I guess. You open that switch in 1 millisecond. The moment you open that switch, this is how it will be. The circuit. This battery is there. This battery is disconnected. That's it. Yes. What will be the current now? The current will be obviously 0. So from this, you have come to this. Here, obviously, the switch was closed. Here, the switch was open. And battery is still there of 12 volts, no doubt. I feel in this process, the current has changed. So EMF has been induced. And the EMF induced in the coil is already mentioned, which is 20 volts. So I think again we have to stick to our original thing. So the average EMF which will be induced, the symbol of triangular brackets means average, is inductance into big change of current in that decently large interval of time. 1 millisecond is not dt, it is delta t. Yeah, that's why I'm using average symbols over here. And I'm not interested in the signs over here. I'm just going to worry about the magnitudes. This EMF induced in the coil is given to be 20 volts. So I'm just going to put 20 over here. L value is exactly what we need. How much is the change in current? Oh my God. Now, I don't know the original value of current, but I think we can find it out. See, whatever this current is will be constant because this current will keep on flowing. There is no growth, no decay, no change of current. So this inductor over here will act like a wire. Why will it act like a wire? I have explained that just some time back. Whenever the current is constant, the inductor behaves like a wire. Oh, brilliant. So I don't have to really worry about that inductor in that scenario. So it's just like a wire, a resistor, a battery, and a switch. What happens? Current is E by R. So battery is voltage by resistance, which means it is 2 amperes. Oh, now I got the point. So original current was 2 amperes. When you open the switch, the current dies out to 0. So the change of the current is 2 amperes. Perfect. In how much time? 1 millisecond. That is 10 to the power minus 3 seconds. That's it. 2 and 2 cancels. We have 10 is equal to L divided by 10 to the power negative 3. So therefore, L will be 10 into 10 to the power minus 3. But this is Henry. Therefore, L will be 10 millihenry. So 10 millihenry is option number C. That is the correct answer. So the trick of the problem was to figure out, yes, the inductor is going to behave like a wire because the current is constant. So we found out the current. Second trick was when you open the switch, the current will drop down to 0. So any change in the current will produce that EMF, which is already given to us. Last step was to actually use that formula and substitute the values to get the answer. Okay, perfect. Awesome. Harish, you are in 9th standard and you can understand the way I teach. Oh, I'm so glad, Harish. That's so great of you guys and probably my teaching. I'm praising my teaching. Okay. And I think I deserve that. Thank you, guys. Can I follow Cengage PYQ books for PYQs? I mean, does it cover? I don't recommend Cengage PYQs. I would recommend Disha publications or use Arihant, that is standard. Okay. It's got most of the PYQs and it's corrected in a much better way. All right. Now that we are done with this, let me tell you that an inductor also stores energy. Okay, an inductor also stores energy. How do I know how much energy does it store? So to get that idea, let's go back to where we started. A mass has that inertial property in mechanics. An inductor has that inertial property in electromagnetism. So, what mass is for inertia in mechanics, inductor is for also inertia in electromagnetism. Correct? Number one. Number 2 point. A moving mass has some velocity. A wire or a conductor or an element or a component will have something flowing through it that will have current. Any change in velocity will be dependent on how much inertia it has. So any change in the current will also be dependent on the electrical inertia which it has, meaning inductance. Okay, that's the second thing. So till now we've thought just like inertia mass over here in mechanics, same way electrical inertia, inductance. Second point, just like motion is measured with velocity in mechanics, here the flow of current, flow of charges is measured by current in electromagnetism. Two things equivalent analogy we have found. Now, when a mass moves, what does it have? It has momentum. Yes. Does it have energy? Definitely. Which kind? Kinetic energy. So a moving mass has kinetic energy. So a current carrying conducting wire or coil or component which has some inductance will also have the energy of motion or the flow, that is the energy stored in the inductor, which is equivalent to kinetic energy of a moving mass. I'll repeat. A moving mass has kinetic energy. Same way, a current which is moving through an inductor will have that energy of the flow of the charges within that inductor, which is producing that flux and everything. That energy in the magnetic form, which is stored in the inductor, that is like the kinetic energy of a moving mass. So that is why we say that, yes, there is energy which is stored in the inductor. So energy which is stored definitely in the inductor. So this magnetic energy is stored in the field of the inductor, and it is analogous to kinetic energy of, or in mechanics, kinetic energy in mechanics. And remember, kinetic energy was half mass into velocity square. So if I ask you how much is the energy stored in the inductor, if it is symbolically given as U, which is like kinetic energy, it will have very similar formula. It will have half. Instead of mass, I will have inductance. Instead of velocity, I will have current. Half Li square. That's it. That's the answer. That's it. Okay. So half Li square in joules is the energy stored, magnetic energy stored in the field of that particular inductor. Very straightforward. Is this absolutely clear? Very analogous. Instead of mass, inertia, inductance is that inertia in electricity. Instead of velocity, you have current. Flow of something, motion of something is velocity in mechanics. Here, flow of something is current. So, current square. Isn't it simple now? Oh, that's great, Harish. You've been following for a long time then. Great, great. Yes, any current carrying wire will have a magnetic field. That was our previous chapter, magnetic effects of current. All right. I I'm so glad. I usually watch all the recorded lives, no issues. We have a lot of people watch my classes recorded. In fact, 90% of the students watch it recorded because right now maybe 10 people, 20 people, 30 people, 40 people might be watching, right? But after a year, when I see the views on the videos and the watch times and everything, it goes in thousands and tens and thousands. So that shows that many students do watch the classes after some time. I mean, 9, can I restart my JEE preparation and complete JEE 11th portion? Yeah, JEE 11th portion, Abhijit, you can finish by February. Definitely. It's definitely a wise move. Okay. Now, I'll tell you, there is something called as energy density also. What does that mean? See, in this inductor, there might be some field, magnetic field. Okay, there will be some magnetic field which is storing that energy. If I take a unit volume, maybe something like this. Chuma, this is just for you to understand, okay? I need not take a cube only, it could be anything else. If I take a small volume, there will be some energy stored in it. So, whatever magnetic energy, magnetic energy which is stored per unit volume, that is then called as the magnetic energy density. Magnetic energy density. Now, unit wise, it is very simple. See, magnetic energy will be obviously in joules and volume will be measured in meter cube. So, joule per meter cube is the unit, SI unit of magnetic energy density. Density symbol is rho, energy I'm using, so U. So, rho U is that symbol of magnetic energy density, joules per meter cube. Now, what might be the formula of it? You might be wondering. I'll give you an idea. I'll give you a hint. Remember electrical energy density? We have studied that in capacitor. Electrical energy density. Electrical energy density. Capacitor stores energy of half CV square, etc. What is the energy density? Half epsilon naught electric field square. Oh, so same formula, but with minor modifications. Like how? You will put half here also. Instead of electric field, which field will you put? Isn't it obvious? You will put magnetic field. So you will put B square. Here in electrical energy density, you had permittivity. Magnetism is associated with permeability. But remember one thing. In magnetism versus electricity, always they go opposites. If permittivity is there in the denominator, permeability will be there in the numerator. If permittivity is there in the numerator, permeability will be in the denominator. Example, like the electric field formula. It is 1 by 4 pi epsilon naught q by r square. Permittivity was in the denominator. For magnetism, what was it? Mu naught by 4 pi I and then dl cross r by r cube. Do you see permeability was there in the numerator? So permeability in the numerator, permittivity in the denominator. They are always opposites. So same logic if you apply here, this epsilon naught was in the numerator. Here it should be in the denominator. So you will see mu naught over here. So this is the magnetic energy density formula, which is very, very easy now to relate with electricity. Is that absolutely clear? Abhijit, I would definitely ask you to complete entire 11th before you go into 11th, because that will be not just good lead, you will finish 12th by 11th, and that last 1 year you will focus on your boards and complete revision and only advanced preparation and Olympiads. That is what your target will be. And do not do 11th in 11th, finish your 11th in 10th only. I mean, at least 90% of it, you can maybe not do some low weightage chapters, okay, here and there, if at all you find scarcity of time, but otherwise you can do it. Okay, that will give you a very good push. That is the best thing. All my topper students have always done that. In 10th standard, they completed 11th standard. Hi, Sai, I'm very good. All right, very good. Amazing. Aryan books are useful for chem and math subjects. No. I mean, for chemistry, yes, not for maths. Okay. Like chemistry, you have your organic part, which is useful. Okay. But other like JDL, you will use it for inorganic if you want to go deeper. And yeah, physical, you can use P. Bahadur, Pittand, and all these things. But other than that, organic, go with um, uh, Arihant books. That is fine. All right. Great. So coming back now, energy stored is half Li square, energy density is half B square by U naught. The last part over here is figuring out how much is actually the inductance stored. Okay, so we will do that. Before going ahead, I will do one more question. Imagine there is in an inductor 100 watts power is lost across a coil, across a coil carrying across a coil of, let's say, um, 25 ohms, of 25 ohms. Okay. Now, what you do is, now the inductor is shorted. Now the inductor is shorted and 50 joules of heat is produced. 50 joules of heat is produced. Question is, find the inductance. It's a very nice question. Many people make crazy mistakes over here or don't understand only what is happening. I'll explain it to you. Read it again. Read it again. Okay. So, yes, DC Pandey books are good. And Abhijit, I can give you a plan. Maybe you can just put up a comment below this video. I will reply to that comment. That will be better. See, there is this inductor and it is having some power loss. Why will it have power loss? Because of resistance. Coil resistance is 25. Where is that resistance? It's an internal resistance, but always internal resistance can be shown as an external resistance. Like for a battery, we show internal resistance slightly outside. That's okay. So this is some internal resistance of that coil of L, and there is some current which is flowing. Why is that current flowing? Maybe because of some battery or something which is connected over here. Okay. Now this resistance is given to be 25 ohms. Current is not given, but how much ever is the power lost, that is given, that is 100 watts. What can I do with that? I can find out the current in it. Do I need that current? Maybe. I don't know. Let's just figure out. We know power is equal to I squared into R. Power is 100. Current square, I do not know. Resistance is 25. So therefore, I square will be 100 by 25, which is basically 4. Therefore, the current will be 2 amperes. So 2 amperes of constant current is flowing. So this is steady state. Steady current is flowing. Steady current is just flowing in the circuit. Nothing wrong in that. Now, what is given? The inductor is shorted. Meaning what? You take out that inductor and you connect the terminals across it. You take out that inductor, internal resistance is still there. Instead of connecting it to the battery, what you are doing, you are just taking these two terminals and you are shorting it. This is the meaning of shorting. So this resistance is still there, 25 ohms. Whatever that current was flowing is also there, but this 2 amperes of current will decay to 0 amperes. That's very important. Why? Because whatever energy was stored, slowly that resistance will eat up, and eventually all that energy stored in that inductor will be lost in that resistor. So during this decay, during that particular decay, the energy which is stored, the energy in the inductor is lost as heat in the resistance. And how much heat is lost? That is given to me. So whatever heat is there, Q, or if you want, you can put any other symbol also. So that heat is energy stored in the inductor, which is half L I square. This is 50. This is half. Inductance, I do not know. Current, we figured out over here, which was 2. Therefore, this 2 and this 2 will cancel. And you will have 50 over here. And this 2 will come over here. This will be L, I believe. So therefore, L will be 25 Henry. That is the answer. This is the logic behind it. Did you love this question? Yes or no? Give me a thumbs up. Smash that like button if you have forgotten. I need to keep reminding you. If you have forgotten to subscribe, please subscribe right away, right now. Great. Hi Sunandana, welcome aboard. 97.5 in JEE Mains and then I scored 19K rank in JEE Advanced. Seedha practice karo tech gaming. I think last time also you asked the same question. Okay. And Abhijit, don't regret. Sometimes reading theory is also a good thing because it gives you a good idea. Now, if you go back to problems, maybe you'll have to just go through quick revision of that theory and you can go on to the problem solving. Yeah, problem solving is the ultimate thing eventually. Okay, don't feel bad. It's okay. Doing theory also is important. But slowly now, go back to problems. I mean, it's not a big deal. We're still in September, October, November. You can easily cover up a lot of things. Major part you will be able to cover up. All right, but don't miss the current classes. That's very important. Okay. Sir, I understood now, sir. What is this? So tell me, how do you exactly measure the inductance? See, I'll tell you one thing. When we started the class only, I told you over here, this property of self-inductance is dependent on the shape, the geometry, the size, whatever materials are inside. So that decides how much is the value of L. It is not dependent on I or phi. Changing I affects phi. L is a completely independent geometrical materialistic property. Okay. So how do I calculate it? So let's take an example of a solenoid, measurement of inductance of a solenoid. So this is our solenoid. And we are trying to find solenoid's self-inductance. What is the self-inductance of a solenoid? All the properties are given. Number of turns per unit length, length of the solenoid, area of cross section, blah, blah, blah. Whatever you need is given to me. Okay, so I'm not worried about that. So let's assume a couple of things over here, like this one. Okay. So the area of the coil is given. The length of the coil is also given. Okay. What else you need? Number of turns per unit length is also given. Small n, which is total number of turns per unit length. So this is turns per unit length. That is also given. Small n. N is the total number of turns. Okay. Now, In order to derive it, go with the fundamentals. Phi is equal to Li. Somehow show flux is proportional to current. Your job is done. Very simple. Phi is proportional to I. So that's what we're going to do. So to calculate the flux, the first thing I'll need is the magnetic field, and I know the magnetic field lines inside are uniform. We have discussed this before. So this magnetic field inside is mu naught Ni. Field inside. If I calculate the flux through any one turn, it will be the field multiplied by the area, which is mu naught Ni multiplied by area. This is flux in a turn. If I calculate the total flux, that will be flux through any one turn multiplied by the number of turns, which will make it mu naught Ni A multiplied by N. But wait a minute, what is N? You can see it right from here. Therefore, N will be equal to small n into L. Small n into L. So instead of the capital N, I'll put small n into L. What is this referring to? This is the total flux in the solenoid. Okay, perfect. So therefore, flux will be equal to mu naught is there, n into n is n square, A is also there, L is also there. I think I missed out on I deliberately. I'll put I over here. Why did I do that? Why did I do that? Observe, guys. You have flux over here. You have current over here. Flux is proportional to current. So whatever is remaining over here, this is that constant of proportionality. Exactly what we want. So hence the inductance will be mu naught n square area of cross section into the length of the solenoid. Now this is something you better remember it so that your problem solving will become quicker and easier, because you will waste time otherwise deriving it. So inductance is the constant of proportionality. Phi is equal to Li. I'm just comparing it. So compare with what? Flux is equal to inductance into current. That's all I'm asking you to do. So immediately you will see this is the inductance. Okay, very simple. All right, perfect. Amazing. Great. So maybe we can solve a question based on this, and here it is. Previous year question on a solenoid's inductance. There is a solenoid which is having total number of turns which is fixed, and cross section is also fixed. However, the length is changed by adjusting the separation between the windings. The induction of the solenoid will be proportional to what length power. Okay, now I'll tell you the weird thing. Why this is a good question also is because of the symbol. You might overlook this fact, but look at this. The length symbol is capital L. Inductance symbol is also capital L. Many students are going to make this mistake. So what I would do as a student in the examination hall, I'll forget that the original symbol is capital L. I will use small l, my original understanding. And I will also relook at the options also like this only. I will look at 1 by L square, 1 by L, L, or even L square. Why did I do it? Why did I change the question? Because I don't want me to get confused in the exam. 100% silly mistake will happen because of these symbols. I've seen so many times they do these small tricks. JEE people, NTA people will deliberately make the symbol confusing. Okay, so be careful. Like I'll give you another example where they choose the velocity symbol as A. Velocity symbol as A. Or acceleration is ax square. 100% mistake will happen. Some derivative integration problem. Acceleration is ax square. A is a constant. What I will do, first thing, I'll replace that A as alpha or put some C or K, so that I know I will not mistakenly take that constant as acceleration. Okay, is that clear, everyone? All right, amazing. Great. So let's start, guys. What is our inductance? Oops, sorry, not this. write this line. Yeah, inductance formula, mu naught, as you can see over here. It depends on the shape, size, number of turns, geometry, material, means permeability and all of that. So mu naught, just use that, n square, A and L. But number of turns is constant and area is constant. So I need to get rid of small n. Small n is nothing but number of turns per unit length. This is A and this is L. So this will become mu naught n square. A is also there. L by L square, that will just become L. So this is inductance, this is length, this is constant. So L is inversely proportional to, this is just our length. This is just our length. It's inversely proportional to the length. So hence B is the right answer, B for Bombay. Is that clear, everyone? You got it? Amazing, right? Don't get confused. Perfect. So these kind of questions can definitely come. There is one more question which can be asked over here. There is a copper wire which is wound on a wooden frame, okay, whose shape is that of a triangle. If the linear dimensions of the side of the frame is increased by a factor of 3, keeping the number of turns per of the coil per unit length of the frame same, then the self inductance of the coil. Now many people got shocked looking at this question. Sir, the self inductance of a triangular coil, we do not know only. No sir, we have to sit and derive. And many students did that mistake of actually sitting and deriving it in the actual exam hall. Many students did that. Yeah. So this is a coil, triangular coil. I'll tell you one thing. Okay. See, simple fact, whatever flux is there will be proportional to the current. This constant of proportionality is L. What do you think this L will have? 100% it will have some permeability will be there, some area will be there, and some, side length will be there, and maybe some constant might be there, 2, 3, n, like that number of turns. These kind of terms will be there in that inductance. Area will be a part of it. Okay, area will be a part of it, just like over here. Just like over here. Where is it? Just like over here. Okay, and that's pretty much about it. Yeah, that's pretty much about it. Some side length, area, and all of that. Now, actually, this side length will also not be there. This will be probably the length or the perimeter or something like that. So some numbers will be there over here. Okay, so might be some length of that coil, something like that might be there. Okay, anyways, forget that. What is important is that area part. See, if the linear dimensions of each side of the frame is increased by a factor of 3, if you change the dimension, what will happen? Think carefully. If you change the dimension and increase it by a factor of 3, what do you think will happen, guys? Come on, answer it in the chat box quickly, everyone. Yes, what will happen? What do you think will happen if all the linear dimensions of the frame is increased by a factor of 3? Yeah, what do you think will happen, guys? What do you think will happen? This area is directly proportional to the square of the side, 100%. So definitely, if side becomes 3 times, this will basically become 3 square times. That means 9 number of times. This will definitely become 9 number of times. So immediately people will say that it will change by a factor of 9, but that is not the correct answer. Keeping the number of turns per unit length same. So I'll tell you what, just like before, here also you will have some number of turns factor. You will also have some number of turns factor involved over here. Okay, number of turns will be there per unit length and all of that. So if you keep the number of turns per unit length same, but you are increasing the dimensions, you are thinking on increasing the dimensions, what will happen to the total number of turns? Just think about it. Okay, if the linear dimensions is increased, keeping the number of turns of the coil per unit length same, okay, if you increase the length, what will happen to the number of turns? Just think about it. Just think about it, my dear students. Yeah. Yes, number of turns will increase or will it decrease? Think about it. Okay. Let's do this in a different way. Let's do this in a different way. If you just happen to measure the magnetic field over here, what and all things will come? Mu naught will be there, some constant will be there, and some current will be there, and the side length will come over here. Mu naught I by R, 2 pi, 2, 4, root 2, some numbers, constants will be there. If you now measure the flux, okay, if you now measure the flux will be magnetic field into area into the number of turns. What is the magnetic field? It is mu naught into some constant into the current divided by the side length over here. Okay, and area is there, so that will have side square, and here we'll have the number of turns. All right. Now, if you rearrange it, how will it look like? Mu naught is there, constant is there, mu naught is there, constant is there, side and side square will cancel. You will have side over here. You will also have number of turns, and then finally you will have the current over here. As you can see over here, flux is directly proportional to the current. So whatever this is my inductance. This is my inductance. Okay. So if you ask me what that inductance is dependent on, mu naught is there, constant is there, side length is there, and the total number of turns are there. What do you think will happen to the total number of turns, keeping the turns of the coil per unit length of the frame the same? This n is going to be, the number of turns per unit length into the total length of the coil, into the total length of that particular coil. Think about it. The total length of the coil is dependent on the side, and this side. So it will be 3 times the side. It will be 3 times the side over here. Is that absolutely clear? So therefore, can you see mu naught is there, C is there, side is there, and this n into L, that L becomes 3 times the side length. So indirectly, L is dependent on the square of that particular side, is dependent on the square of that particular side over here. So if you change this side by a factor of 3, what will happen? 3 square is nothing but 9. So this will increase by a factor of 9. Is that absolutely clear now? Okay, this is an English channel, that's why we speak in English. That's all. We already have so many Hindi channels. We don't have English channels at all. Got it? Everybody with me? Let's go to the final part, which is the combination, which will talk about the combination of inductors in series and parallel. It's very laddu only. If inductors are connected in series, then what happens is all the inductors will have the same current. This current will be same. So the current is going to be the same, but it is the EMFs which will be different, and the net EMF will be EMF across 1 plus EMF across 2 plus EMF across 3, like that. Correct? What is EMF across the first inductor? Use the formula L di by dt. Yes, inductance into di by dt. EMF across the second inductance will be second inductor's value into rate of change of that current. Like that, so many terms will be there. The net EMF in that net inductance will be the net inductor value, which I will call it LS, into di by dt. Why is the current same everywhere? Because it is in series, so current is going to be the same. That is only the reason why this di by dt will cancel everywhere, and that's why you will see the effective inductance in series is like resistors, L1 plus L2 plus L3, like that till Ln. That is the answer. That is the answer. Okay, very, very important. The total net effective inductance is L1 plus L2 plus L3, like that till Ln. Is this absolutely clear? Okay, perfect. Okay, amazing, 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 amazing. Great. Now, what if they are in parallel? One can easily guess the answer. The EMF or the voltage difference is same. The voltage difference is same. It is the current, the net current, which will get distributed as I1 plus I2, like that. So therefore, the net current rate also will get distributed. That will be di1 by dt plus di2 by dt, like that. And what is rate of change of current going to be? Logically speaking, EMF is L di by dt. So therefore, di by dt will be EMF by L. It will be EMF divided by L. So that's why when you put E divided by L1 here, this will be E divided by L2 over here, and so on and so forth. This is the net EMF, okay, which is the same, by net inductance, which is LP. You will see now this E will get cancelled everywhere, and that is why it will behave like resistors in parallel. So 1 by net inductance in parallel is 1 by L1 plus 1 by L2, like that, 1 by Ln. Very logical and simple. So there is nothing great about this. I mean, it's just like resistors in series or resistors in parallel. Just like that same concept, in parallel voltage is same, current will distribute. In series, current is same, voltages will be spread across the devices. That's all. Okay, William, this is the last session of inductance. Okay, we'll come to this combination in a bit. I mean, there is nothing great that you can do in these problems, like just asking what is the net inductance and all of that. It's a very laddu type of question. I mean, like say for example, somebody gives you a question like this. There is an inductor here, and an inductor here. This is, L, this is 2L, and let's say this is 3L. And they tell you, listen, I'm connecting this with this and this with this. Can you find the net inductance? How much is it? Well, definitely we can. These three inductors are actually in parallel. This is a disguised circuit. You have seen this in resistors also. So strictly speaking, this is one inductor here, another inductor here, and another inductor over here. This is L, this is 2L, and this is 3L. So now we can find out the net inductance using this formula. They are in parallel. So it will be 1 by L plus 1 by 2L plus 1 by 3L. So LCM is basically 6L. So 6 plus 3 plus 2. 6 plus 3, 9. 9 plus 2 is 11. So 11 by 6L. That is 1 by LP. So LP will be 6 by 11 times of L. So that is the answer. So all these kind of problems can be easily done. Nothing great about it. Okay. All right. Is that understood, everybody? Okay. Perfect. Perfect. Let's move now to the next and the final concept of mutual inductance. We have studied self-inductance. Now we'll study mutual inductance. What is this mutual inductance? I just mentioned it to you that mutual inductance means you are affecting the other coil. Any change in you will create something in the other coil. So in mutual inductance, there are two coils. One of them is called primary, where the change in the current happens. The second one is called secondary, where the effect is being felt. Primary is where the fluctuation in the current happens. Secondary is where the effect of the primary is being felt. So there are two coils. So I will call this as my primary coil, which is connected to a battery, and this one over here is my secondary coil, which is going to feel the effect of the primary. Now in the primary coil, as you can see, there is a battery and everything, and maybe some kind of current is being passed. So this current is being passed. This current, when it passes through the primary coil, it will produce a magnetic field. Some of the magnetic field lines may just go out. Some of the field lines will just pass through it, something like this. So there will be some magnetic field due to primary coil. This is very important. Due to primary coil. Out of those magnetic field lines, a few of the field lines will pass through the secondary coil. That will create the secondary flux. That will create the flux in the secondary. So there will be a flux. What is this? This is nothing but a flux in the secondary coil. Flux in the secondary coil. Now this is the whole game plan. Imagine if the current 1 stands for primary, 2 stands for secondary. Primary current changes. Primary current is changed. What is the direct implication? So this is the first thing which I'm doing. I'm changing the current in the primary. The immediate effect will be the magnetic field, the field due to the primary changes. The field due to the primary changes. Due to which the flux in the secondary coil will change. The flux in the secondary coil also will change. And once the flux changes, we know by Faraday's law, EMF is induced in the secondary. This is in accordance to Faraday's law, and the direction is to oppose the change. Direction is to oppose the change, which is as per Lenz's law. So this EMF, which is produced in this coil, opposes this current's change. It does not like this current changing. This guy is telling, this is like a friend. You are trying to change. This friend is telling, don't change. That is then called the mutual inductive property. Yeah, this is then your mutual inductive property. Is that okay? So this is now your mutual inductance. This is now your mutual inductance. I hope this is absolutely clear. And now we can figure out how much is that mutual inductance and how much is the value of that mutual inductance and everything. So let's have a look at it. All right. First of all, let me start blocking these things. Okay. So here is the logic. The flux in the secondary, is dependent on the current in the primary. So I will say it is proportional to the current which is there in the primary. I don't want that constant of I don't want proportionality. I want a constant of proportionality. So I will write down over here equal to, and I will put M. This is called mutual inductance. This is called mutual inductance. Very, very important. Okay. Now some of you will be like, sir, but wait a minute. You made this as primary, this as secondary coil. What if I pass the current here and then made this coil as the secondary? The answer will still remain the same. So it's not like if you change the roles played by the coil, the mutual inductance changes. No, nothing like that happens. This is also very, very important. So say for example, the roles which are being played. So phi 2 is M I1, but here if I put phi 1 is M times of I2, this M happens to be the same. So mutual inductance between a pair of coils is same irrespective of which one is primary or secondary. So it really doesn't matter. You can choose as per your own convenience which one is primary or secondary. The mutual coefficient of inductance is the same. Okay, this is very, very important. Okay, so having said this, first of all, again, let me just block this off. It's obvious that it again depends on shape, size, etc. Shape, size, material inside, etc. It does not depend on the current. Also, again, the SI unit will be Henry only. There is no difference. And just like before, this will be Weber per ampere. Weber per ampere. No difference at all. Okay. Lastly, if you differentiate this, you will get d phi 2 by dt will be nothing but equal to m times of di1 by dt. So if you notice, this is di1 by dt. This is your mutual inductance. What is this d flux change with respect to time? This is the EMF which is induced. So this is the induced EMF in the secondary coil. This is the induced EMF in the secondary coil. Just like before, I'm just talking about the magnitudes over here. So let's not worry about the directions. Okay, so this is the magnitude of the induced EMF in the secondary coil because of the changes of the current in the primary coil. That means if the current changes here, how much EMF will be produced over here? That is what we are talking about. Okay, just like before, there is not much of change. All right. Now, having said that, we can also find how much is the mutual inductance. And one second, where is it? Let me give you a question first, and then we'll go ahead. So, imagine if the current in coil 1 changes, or I will put coil A to avoid confusion. Coil A changes by or changes from 1 ampere to minus 3 amperes in 2 seconds. An EMF of 10 volts is produced in B. Now, a current of 2 amperes changes to 4 amperes in 10 seconds in sorry in 0.1 seconds in 0.1 seconds in coil B, find EMF in A. Very nice question. Let's try to think about it. Let's understand the first scenario. This is coil A, this is coil B, assume. This is coil A, this is coil B. This is primary. This is primary. This is secondary. Okay. In coil A, the current is changing this much. An EMF is produced in coil B. Okay. So if I use my formula, E2 is mutual inductance into whatever, di1 by dt. Remember, this was our formula, which I told you over. E2 is m di1 by dt. Okay. So this EMF is already given to me. It is 10 volts, mutual inductance not given. Current is changed from 1 to -3. So how much is the difference? The difference is 1 minus of -3. I'm only interested in the magnitudes, remember that. And time interval, I think it is also given in 2 seconds. So this will be m multiplied by 4 by 2, and this is 10. This will be 2. So therefore, m will be 10 by 2, which is 5 Henry. So the mutual inductance is now 5 Henry, which we got. Use this for the second part. The second part is where the roles get reversed. Where now this A and B, this B becomes your primary. Current changes in B and A becomes your secondary. Voltage is induced in coil A. So now E1 is M times di2 by dt, like that. So mutual inductance, we figured it out to be 5. How much is the current changing? From 2 amperes to 4 amperes. So the change is modulus 4 minus 2 by the time, which is 0.1 seconds. It's mentioned over here. So 5 multiplied by 4 minus 2 is 2. 2 by 0.1, that's going to be 20. So that's going to make it 100 volts. So that is the EMF in that coil, 100 volts. Is that absolutely clear, everyone? Amazing, amazing. Is that cool, everybody, till this point? Oh, amazing. Right. Great. Let's move now to how do we find the mutual inductance, and let's take the example of concentric solenoids. So example of concentric solenoids. Concentric solenoids. Here we will take the outer solenoid to be our outer one to be primary, and the inner solenoid to be the secondary solenoid of the secondary circuit. Why like that? Because I know if I take a solenoid, calculating the field inside of it is easier. Outside the field is zero or negligible, which I don't know. So better to take the calculations for inside of a solenoid. So we make current passing through the outer solenoid. Okay. So the primary solenoid will have number of turns N1, length L1, okay, and whatever area A1. The inner solenoid, the secondary one, will have number of turns N2, length L2, area also A2. Now ignore the actual diagram because it feels like, you know, the inner solenoid is coming out of the outer solenoid, and if you look at it closely, then you will realize the field lines will become non-uniform, which shouldn't be the case, becomes very complex. So we will assume that the outer solenoid which is the primary one, is long enough. Okay, I have not shown it here, but just imagine it is long enough. They are both long enough solenoids. And anyways, we don't study short solenoids, we always study long solenoids. So the field lines are uniform as such. Okay, so what will we do now? First thing, we'll calculate the field due to outer solenoid. What is the field inside the outer solenoid? That will be, because of the primary one, B1 will be mu naught Ni. N will be N1 and I will be I1. Okay, perfect. So that field will pass through the coils of inner solenoid. So the flux in a coil, which will be phi1, will be B1 into the area of the inner solenoid, which will be A2. So therefore, if I mention the total flux in the inner solenoid, that flux will be, that particular flux will be whatever that phi1 is, you multiply it n number of times. How much number of times? N number of times, number of turns, because there will be n2 number of turns. So now it's just a matter of substitution. So phi will be phi1 is nothing but B1 into A2 multiplied by N2. What the hell is B1? B1 is right over here. You can see that, which is mu naught into N1 into I1. A2, I'll just keep it as it is. Number of turns 2 can be written down as N2 multiplied by L2. Why so? Because this N2 will be capital N2 by L2. So therefore, capital N2 will be small n2 L2. Is that clear now? So capital N2 is small n2 L2, number of turns per unit length. So let's rearrange this flux, which is there in the secondary. This is the flux in the secondary. Flux in the secondary coil will be mu naught is there. I think N1 is also there, N2 is also there, area is also there, length is also there, and just one single current is left out. Deliberately I did it. Why? Because now you can see my flux in the secondary is directly proportional to the current in the primary. So whatever is over here is the mutual inductance. So the mutual inductance is mu naught N1, N2, A2, L2. That's it. That is the final answer. Is this absolutely clear, my dear warriors? Mu naught N1, N2, A2, L2. Very similar to the solenoids formula right over here. Compare this formula with this one. Mu naught Nn Al. Nn is n square. So here it is just n square. So you split that n square into N1, N2, you will get the same thing. Mu naught N1, N2, A2, L2. Okay? Clear, guys? It is dependent on the material, the turns, the shape, the size, everything, geometrical aspects. Sometimes you might not be given a solenoid, you might be asked to find, let's say, what is the mutual inductance of two circular loops which are in the same plane, two circular coils or something like that. The mutual inductance between them is how much? So diagram is not shown, but I can draw it, not that difficult. Two coils are there in the same plane. The logic is exactly the same, guys. A and B are placed in the same with the centers coinciding. The mutual inductances, I'm not sure which coil is bigger, which coil is smaller. It's not given. I will just take this as A and this as B. And what I will do, I'll take this as my primary coil and I will take the inner coil as secondary. This choice is very important. Why did I do that? Because finding the magnetic field due to the outer coil at the center is easier. but I do not know how much field this coil will generate at this point outside the coil. I don't know that. So this choice is very important, else you will be stuck. So if you ask me, the field, the magnetic field at the center, how much will it be due to the primary? It will be mu naught, number of turns, just one, I guess, one circular loop. I is I1, some current will be going over here, divided by 2R, radius is nothing but B, that's it. So then if you ask me how much flux is there in the secondary coil, that flux will be the field multiplied by the area, The field is mu naught I1 by 2B. The area is the area of this particular coil, because how much flux is going through this part. So that will be pi A square. So therefore, this flux is mu naught pi A square by 2B, and there is I1 over here. Clearly you can see this flux is proportional to the primary current. So whatever is over here, this is only the mutual inductance. Phi is Mi. Okay, so phi is Mi, that's it. So that is the answer, mu naught pi A square by 2B. Mu naught pi A square by 2B. So whenever you see that the flux is proportional to the current, that constant becomes the coefficient of inductance. That's all you have to do to find out how much it is. These kind of questions are very famous. In fact, I will give you one question as homework. Try to do this question as homework, okay? So I want everybody to solve this as your homework question. And post the answers in the comments. Post the answers in the comment section. Okay? Very good. Very good. Excellent. Yeah. Mu naught is permeability. Yes, my dear. Mu naught is permeability. Perfect. Now, there is one last concept which I want to touch upon. When you combine self-inductance with mutual inductance, what to do? Okay, some questions might come like that. Like, say, for example, I have two solenoids or two coils placed near each other. If they are far, then they will not affect each other. But if they are close by, then there will be also mutual inductance. This M is when they are close to each other. So when I combine them as one single inductance, effective inductance, how much will it be? I'm converting this entire scenario into this. How much will it be? What do I need to do? So I'll tell you what, in such scenarios, what you should do. See, imagine there is some kind of current which is passing through it. That same current will also pass over here, isn't it? Whenever there is a change in the current here, there will be an EMF which will oppose it. Assume the current is increasing, so that EMF will try to oppose that change. So I will try to convert all these inductors into batteries and then combine those batteries into one single battery. That's what I will try to do. So first of all, this particular inductor, then this particular inductor, okay, then this inductor will affect this inductor, and this inductor will mutually affect this inductor. So like that, four things will be there, four batteries will be there. That is the first concept in these questions. When you consider the current in this particular inductor self-affecting itself, it will behave like a battery like this. That EMF will be L di by dt. If this current is increasing, it will produce an EMF to oppose that change. It will not like that change, so it will oppose it. It will behave like a battery like this. That same current is passing through the second inductor. This was, remember, L1. This was, remember, L2. That change will again be opposed by an EMF, and that EMF will be L2, same current di by dt. Because the current is changing in this coil, do not forget some of the flux will also go through the second coil. There will be a mutual property. So that same flux, keep this in mind, whatever flux will go over here, some of it will definitely pass through this. Some of it will definitely pass through this. That will also produce an EMF over here. How will that EMF be? Think about it. Whatever the coils are, they are oriented in the same way. So if the current tries to increase, this coil will try to oppose that change, meaning that EMF will also be in the opposite direction, but it will be M times di by dt. M times di by dt. It is also trying to oppose that change. The current increases, the flux increases, this inductor mutually will oppose that change. Same logic I can say here. Because there is some current over here, there is some magnetic field passing through this inductor. Some of the flux is passing through the first inductor. So if any increase of the current happens here, the flux here will increase. That will be again opposed by this. It will oppose it, meaning consider another battery opposing that change like this. So M times di by dt over here. So now we have 4 batteries, 2 due to self, 2 due to mutual. Mutual why? Because this will affect this will affect this. Both of them will oppose the increase of the current in the same direction. So if you combine all of these batteries, exactly you have now 4 such batteries in series, which has to be combined into one single battery for the effective inductance. So that's it. So L effective di by dt will be nothing but L1 di by dt plus L2 di by dt plus M di by dt plus M di by dt. Di by dt will cancel. So what am I left with then? L effective will be di by dt will cancel. I am just left with L1 plus L2 plus M plus M plus M plus M, which is L1 plus L2 plus 2 times of M. That is the answer. L1 plus L2 plus 2 times of M. Is this clear? Very interesting concept on how self and mutual inductance, especially when the coils are close by, will affect each other. This 2M has come because each one of them will affect the other. I'll tell you, this is okay. The best question is over here, which was asked in JEE 2022. Look at these coils, and the question is, what is the total inductance of the combination? Many students thought it is just like the problem we solved. So what they said was, sir, they are in series. So there is one battery like this, self-inductance L1 di by dt, and also L2 di by dt. And then they use the mutual inductance concept, and they connected 2 more batteries just like this one. And they thought the answer is L1 plus L2 plus 2M. L1 plus L2 plus 2M, which is C. But that is wrong. Reason being, look at the manner in which the coils are connected. When the current goes, it comes in the opposite direction. So when the current increases, the flux is already going in the opposite direction. So if the current increases, the flux increases in the opposite direction. So actually the EMF will come in the same direction as of the current. So the mutual inductive EMF will actually be assisting it. So M di by dt will come 2 times, but in the same direction. This is the crazy part of this problem. Yes, if this is the current, this current is going like this. And why has this happened? Because the coil is flipped and connected like that. The windings are opposite. And now, if you combine them, Obviously, this one be plus, this one will be obviously minus because they are opposing this direction. So if you ask me the net, if you ask me the net, whatever, uh, inductance, so the net inductance, that will be L1 plus L2 minus 2 times of M, or minus M minus M, which will give me this as the answer, L1 plus L2 minus 2M. Lot of people wrote C option, that is wrong. So the catch was the coil is connected in the opposite way. Yeah. All right. Absolutely clear. Okay. Amazing. Amazing. So that was the last question which we had. I hope you enjoyed the class, and we did a lot of questions out here. A big class, but a very, very comprehensive class, right from the basics to the proper advanced level, right? So make sure you are downloading the notes. It will be there in the description box or in the comment section by tomorrow. Also, like the video if you have not liked. Comment the homework answer, which I've just mentioned some time back. Solve the homework question. It is a previous year question. And post the answer in the comment section, and let me know whatever doubts you have or any concerns. Just put it up in the comments. Okay. So good night. Have a great time. Bye bye. God bless you all.